I realize some of you might not be totally finished, but let's take a look and see how you're doing on these so far. Now, these are not easy problems because the standard procedure is to start with the doctor's order and work through from that to figure out what to administer to the patient. Well, here we're not given the doctor's order. We're asked to work kind of backwards. So what we have to look at is we have to look at what units, what form we want our answer in to figure out what we really need to start with. And number one here, everything that we're given is an equivalency. 36 drops is equivalent to 1 minute, is what that's telling us. 15 milligrams is equivalent to 8 milliliters. 9 drops is equivalent to 1 milliliter. Those are all equivalencies. They can be used as conversion factors. We do have to start with one of them, so we look at our result. We want our result to be in milligrams. So we want to start with something that has milligrams in the numerator on top. And we're going to leave those milligrams alone all the way through to our answer. What we have there that has milligrams in the equivalency is 15 milligrams in 8 milliliters. So I'll put the 15 milligrams on top because we want to keep them there. 8 milliliters on bottom. Now we want to keep the milligrams. We don't want to get rid of that. But we do want to get rid of the milliliters. So I'll put milliliters on top. And let's see what we have with milliliters in it. This is saying 9 drops is equivalent to 1 milliliter. So 1 milliliter is 9 drops. So now we've canceled out the milliliters. Right now we have milligrams per drops. Want to get rid of drops. Drops on top. We do. The only other thing we have here that has drops in it is the flow rate of 36 drops per minute, which is saying 36 drops is equivalent to 1 minute. That cancels out the drops. We now have milligrams per minute, which is, believe it or not, getting us closer to our answer. We do have one value here that is not part of equivalency, and that is the 6 hours. We can use that 6 hours to cancel out time. And right now we are in milligrams per time, but the time we have is minutes. So we want to convert our minutes to hours. 1 hour is 60 minutes. So the minutes cancel out there now, leaving us now with milligrams over hours. Now that we have that, time is given as 6 hours. We can just multiply by 6 hours over 1. This should tell us then the amount of milligrams. Hours have canceled out. Now again, if I were doing this on my own, I might be tempted to cross cancel, but there aren't really huge numbers here. So I'm just going to multiply through on the top. We've got 15 times 1 times 36 times 60 times 6 gives us 194,400. That is in milligrams. On bottom, we've got 8 times 9 times 1 times 1 times 1. 72. Divide by 72. 2,700 milligrams. Any questions on that? Just out of curiosity, how many of you came up with that? Couple? That's not one of the easier problems that we've done by any means. I probably wouldn't be quite that harsh on you on a test, but there will be a couple of problems on the test where we are working backwards, trying to find what's the drop factor, what is the volume infused, and stuff like that. So for number 2 here, similarly, pretty much everything we're given here is a rate. Remember, anytime we have a rate, it can be used as an equivalency. But right at the very beginning here, we have 2,500 milligrams over 6 hours. That is a rate. That is telling us 2,500 milligrams is equivalent to 6 hours. Infuser is set 40 drops per minute. So 40 drops is equivalent to 1 minute. 16 drops per milliliter. 16 drops is equivalent to 1 milliliter. We want the concentration of our solution. Concentration is given in milligrams per milliliter. So I either want to start off with something that has milligrams in the denominator or in the numerator, something with milligrams on top, or I want to start out with something with milliliters on bottom. Either one will work here. I'm going to do it actually both ways. I'm going to start out with the milligrams on top. So we'll do this version first. And what we have that has milligrams on top is that order. 2,500 milligrams over 6 hours. I want to leave the milligrams alone. I want milligrams in the numerator of my result because the units have milligrams in the numerator. Need to get rid of hours. I don't have anything else up here that's in hours. The only other time I have is minutes. So let's convert our hours into minutes. 1 hour, 60 minutes. About the hours. So now to get rid of the minutes, we want to get to milliliters in the denominator. So let's get rid of minutes. Our relationship here is minutes. So saying 1 minute equivalent to 40 drops. Current flow rate. So now what we have is milligrams per drop. Our next step, then we can take that, putting drops on top. You have 16 drops per 1 milliliter. Drops will cancel out, and we're going to have milliliters on bottom, which is what we want. Milligrams in the numerator, milliliters in the denominator. So we'll multiply this out. 2,500 times 1 times 1 times 16 is that 40,000? Over 6 times 60 times 40. $14,400 liters. Check my. So now I just have to divide that out. 40,000 by 14,400 at 2.78, 2 7/9 technically. Milligrams per milliliter. Now the reason that doesn't look real familiar is the way we would normally see that is we would try to get rid of that fraction. That would normally be written as 25 milligrams, 9 milliliters, so that we don't have to have the decimal in that. But this is still a valid concentration. Now I said we could have started with milliliters in the denominator because we want milliliters in the denominator of our answer. Let's think about doing it that way. We have 16 drops per milliliter, so we can start with that drop factor. Can everybody see that on the bottom of their screen, or should I scroll up a little bit?
No, that's good.
So we want to keep the milliliters. We're going to get rid of the drops. The only other thing we have here that has drops in it is the 40 drops is equivalent to 1 minute. Equal to 1 minute. Canceled out the drops. We have minutes per milliliter right now. We're going to get rid of the minutes. We don't have anything else with minutes in it. We have stuff with hours in it, so we're going to convert our minutes into hours. And now we can equate the hours. 6 hours is equivalent to 2,500 milligrams. Hours cancel out. You'll notice here that we have the exact same numbers on top. 16 and 2,500 still multiply up to make 40,000 milligrams. And on bottom, 40, 60, and 6, 1,000 or 14,400 milliliters. And of course, that'll divide out to give us the same concentration. Both of these problems are maybe a little bit tougher than I would ask on a test. But they're both great examples of how I don't need to know anything about the formulas that govern these materials. All I have to know is what units I want my result in. Up here, I knew I wanted it in milligrams. Here, I knew I wanted it in milligrams per milliliter. And I use the units of my result to formulate my plan to get there, figure out what I want to start with. And then it's just a matter of using those equivalencies and the dimensional analysis, the unit conversions, to convert what I have into what I want the answer to be. There are formulas for both of those processes, but they're very different formulas, and the formula varies depending on the information given. Are you starting with milliliters per hour, or milliliters over hours, or are you starting with milligrams over a number? That alters the formula. So being good with that dimensional analysis pretty much solves everything to do with those IB calculations, any of our dosage calculations. Okay, so where we left off last week, the last thing we were doing was dosages based on weight. So I'm going to review one of those before we move on. So let's say we have an order to administer recommended dose every 6 hours. So our supply, the label says to give, bless you, 80 to 100 micrograms per kilogram every 8 hours. And the label says it's constituted 16 milligrams in 9 milliliters. So we want to find what dose you will administer to the patient. Study the patient. We're going to have a patient that is 5 pounds. You may tell me what the first step is.
Convert to 55 pounds.
Perfect. Convert 55 pounds to kilograms, which gives us 25 kilograms, divided by the 2.2. Starting out with a 25 kilogram patient, what is the next thing we need to do? Let's say we're going with the max first for our initial calculation. What do we do next? We need some sort of kilograms on bottom. What goes on top here? 100 micrograms per 100 micrograms per kilogram. Now there is an extra step in this one because the concentration is milligrams per milliliter. This is in micrograms. How do I get rid of those micrograms and convert it to milligrams? That's my relationship. Which one's larger, milligram or a microgram? Milligram is the larger one. So we always want to put the one with the larger one if we can. Micrograms are the smaller one, which means there's going to be a large number of them. Metric system, that conversion is pretty much always 1,000 if we're sticking with our main unit. Cancels out the micrograms, we now have milligram. Now we can convert milligrams to milliliters. So in this next conversion, what's going to go in that factor? 9 milliliters on top, 16 milligrams on bottom. So the milligrams cancel out. So now we can go ahead and multiply this out. 25 times 100 times 22,500 milliliters. Yep. And on bottom we have 1,000 times 16,000. 22,500 divided by 16,000 going to give us 1.406. So we're going to call that 1.41 milliliters. Now, what do we have to remember to attach to this at this point? Time frame. And the time frame we need to put in here is per how many hours? Careful. 8. Recommendation is off of 8 hours. Now, the doctor did order to give this every 6 hours. So we're going to have to adjust that. That's where we use that titration. So this is 140 or 1.41 milliliters. That was calculated using an 8-hour dosage spacing. And we're converting it to a 6. Remember, what we've calculated is on bottom. What we're going to is on top. So 1.41 times 6 divided by 8 is this 1.057. So that's 1.06 milliliters every 6 hours. Remember, that was our maximum dose. We had used the largest recommended dosage for that. Still need to find the minimum dose. That's the maximum dose is 1.06 milliliters. That was calculated using 100 micrograms. We want to convert it to the 80. So again, what we've used for this calculation goes on bottom. What we're converting it to goes on top. 1.06 times 80 divided by 100, 0.848 or 0.85. Milliliters every 6 hours. Minimum. So that's our range, 0.85 to 1.06 milliliters every 6 hours. Any questions there? So using a patient's weight is one of the ways to calculate a recommended dose. There's one other, I don't want to say common, but another viable way of calculating dosage, depending on what the medication is for, is body surface area. This is used when you're doing medication for skin conditions, often used for burn victims and other related situations. Body surface area is always calculated in square meters. Now remember, a meter is slightly bigger than a yard. A meter's just under 40 inches. So you're looking at 40 inches by 40 inches. That's a pretty big area for a single square meter. So people are going to be, 2 square meters is a rather large person for body surface area. So keep that in mind as we're doing these calculations. So to calculate, we need to know what units we're starting with. Rather than having to convert our units all into metric, we do have a formula to calculate if we start out with standard measurement. So for standard measurement, height in inches and weight in pounds. The formula: body surface area in meters squared is square root of height times weight over 3,131. (3,131) is just a constant that was developed based on the units for height and weight, and then to get it to the appropriate body surface area. So if we have a patient who is 70 inches tall, 180 pounds. Body surface area, 70 times 180, 3,131, and then square root it. Most of your calculators, you can do this all in one calculation. Square root, many of you have to use a second or a shift key to get your square root. Then you just type in, if you have the two-line display calculator, then you can just type in, it should give you a parentheses after your square root, or like mine, it puts it inside the square root symbol. Just type in 70 times 180 divided by 3131. Nothing to do special for the fact that that's divided for that last number. Many of you would have to close your parentheses at the end of your square root here. Right, 2.006. We almost always round to 2 decimal places. That'd be 2.01 square meters. Now, if you don't have the two-line display, I see a couple of you have the one-line display calculator. The square root is the last thing you have to do. You type in the 70 times 180 divided by 3,131. You hit equals, and then you hit your square root key. Did everybody get that 2.06 or 2.006 or 2.01 meters squared? Anybody need help to get their calculator to do that? Good. If we start out with metric units, so we have metric units. We're looking at our height in centimeters and our weight. Of course, we know it's not really weight, it's mass, bless you, in kilograms. So we're still calculating our body surface area in meters squared. Formula is still height times weight, but because the units are different, because it's centimeters and kilograms, it's over 3,600. That's the only thing that's different between the two formulas is that constant that's on the bottom of that fraction. So let's say that we have a patient that is 190 centimeters tall and 90 kilograms. Body surface area will be 190 times 90 divided by 3,600. Square root. Second square root. 190 times 90 divided by 3,600. 2.16 0.79, which we will round 2.18 meters squared. Any questions there? Have you guys try a couple in your notes. So patient 1 is 74 inches tall, 210 pounds. Patient 2, 185 centimeters tall and 100 kilograms. Find the body surface area for each of them. We'll go over it in about a minute. So our first example here, both of those are standard units. So it'll be 74 times 210 over 3131. Which gives us 2.227, round it 2.22 or 23 square meters. Patient 2, these are both in metric units, so it'll be 185. A bit larger, there we go. 185 times 100 divided by 3,600. That's 2.27. Any questions? So the 4 examples I've used so far are fairly large people. I mean, we said 2 square meters is a pretty big person. All of these have been over 2 square meters. The reason I've used those numbers for this calculation is the alternative method, which is a nomogram, is not able to be used, at least the one that we have that we're going to use, is not able to be used for those large people. A nomogram is a graphical way of calculating things, where you have 2 values. In this case, we have height and weight, and you plot them on a scale. So maybe the person has their height here and their weight there. You connect those 2 values from those scales, and in the middle, somewhere, you have that body surface area. So wherever that line crosses the scale on that body surface area, that is the amount for that patient. Nomograms are used in a lot of things to cross between, a relationship between 2 values and to find what that would equate to a third value. So the nomogram that's in our textbook looks like this. Now this nomogram here, because of the way it had to be spaced, notice we have height here and weight here. And surface area, body surface area is right there. Those columns make up the whole nomogram. This here is really not part of the nomogram. But in order to make it work out, the surface area had to be a lot closer to the weight than it was to the height. So there was a big space here in that nomogram. So what they did was they inserted this little table into that space to make use of it. So we just didn't have that big extra space. But for what we're about to do, we ignore that piece of it right now. We're not going to use that until later. So if we're looking at a patient who is let's go 49 inches and 92 pounds. Choose the nomogram to find their body surface area. So for height, we need to find 49 inches. So if we look up here, inches are on this side, centimeters are on this side. I have no idea why they go up to 90 inches. Don't know too many people out there that are 7'6", but yeah. So we had 49 inches. Looking at this, that's actually 48 that I just marked. Nope, that'd be 49, sorry. This is 45, 6, 7, 8, 9, 50. So that is the 49 inches right there that I just put that brown dot. Now we needed 92 pounds. So over here on the weight, we've got to find the pounds. Pounds are on this side for weight. So here's 90, there's 100. This is going to be a little less precise because it's just 90, 95, 100. So 92 we know somewhere in between there, probably a little closer to the 90. Now in practice, I would take the edge of a piece of paper or a ruler and lay across this. This is on the computer screen, you wouldn't be able to see that. Try to draw a line across here. Change that line a little bit so you can see it better. I don't want to make it too thick, otherwise then it's not very precise. But anyway, so you can see we've got that line connecting from 49 inches to 92 pounds. So now when I look at our surface area here in meters squared, we see this is 1.2 and this is 1.3. We're really close to that 1.3. I'd say like 1.28 or 1.29. We're going to say 1.28 meters squared is what that patient come out to be. So 1.2 meters, 28 meters squared is our approximation off the nomogram. Let's calculate it out using the formula to see what it would come out to be. So if we use the formula, that'd be the square root of 49 times 92 over 3,600 or 3131? 3131. Give us 1.20 square meters. So the question is, which is a better estimate? Both of these are estimates. The formula, however, is more consistent. Look at the nomogram, there's a lot of things that had to happen. First thing I can see right here is I probably had this dot for weight a little high. Looks like it's a little closer to the 95 than the 90, so that probably doesn't really accurately represent 92 pounds. But we'll be able to slide that down and fall or not. No, it won't let me. Not gonna let me move it that precisely. There we go. You can see that brings it down a little bit. Although on the other end, I might be a little low over there. So it's still a little off. The nomogram is not as accurate as the formula. It's just a quicker way of doing it. And if you don't have a calculator, square roots are pretty hard to do by hand. Let's do another example here using metric measurements for the nomogram. So let's say we have a patient who is 160 centimeters and 40 kilograms. So over here, 160 centimeters. Centimeters are on the left side, so I'm going to move my line up here to 160, right about there. What did I say? 40 kilograms. So 40 kilograms are on the right side over here, so we're trying to get that to go through the 40 kilograms. Right about there is where it goes through. On our nomogram, that's between 1.3 and 1.4. Maybe slightly below 1.35. Looks like probably 1.34. Let's go with that, 1.34 for now. Let's double check that with the formula and see how close we got. So 160 times 40 over, which constant do we need to use? 600. 1.33. That was almost dead on. Generally, the nomogram is much closer for metric measurements. I don't know why, but it just seems to work better. Now, I mentioned there's a weakness with the nomogram. And this one, I always chuckle. I don't know why it does this. But the height goes up to 7'6". Don't have to worry about height. Anything from 14 inches, 7'6", we're covered. But for weight, goes down to 3 pounds, only goes up to 180. That leaves a lot of people off the charts for weight. So we can't use it for people above 180 pounds. Which brings us to this little inserted table in the middle here. It does have a use. That is for pediatric body surface area. Notice it says for children of normal height for their weight. So if they are height-weight proportionate, this can be used by simply using their weight in pounds to find their body surface area. So if we have a patient who comes in weighing 60 pounds, that's 60 pounds right there. All we do is look at the other side. This is 0.9, that's 1. This would be 0.95. I'd say that's somewhere around like 0.98, 0.99 is where their body surface area is coming. So if they are relatively height-weight proportionate, we can approximate their BSA rather quickly off of that. The nomogram is in your textbook. It actually appears twice on 2 separate pages, back to back. Page 192 and page 193. I looked at them. I didn't see any obvious differences between the two of them, but there. So if you have your book in front of you, I want you to try do 2 patients here again. So for patient 3, we're going to do 71 inches and 170 pounds. Patient 4, we're going to do 120 centimeters and, let's go 38 kilograms. Find the body surface area using the nomogram for each of those patients. It's harder than it looks to try to line that up on both sides. I will sometimes, if I have a very fine tipped pen or pencil, I'll put that down on one side so that I can pivot off of that so I don't have to worry about trying to hold. So that first patient was 71 inches and 170 pounds. 71 inches. Right here. £170 up here. That person, I'd say really close to dead on 2.0. Is that what you guys came up with? Somewhere in there? 1.99, 2.0. Patient 2 was 120 centimeters. And 38 kilograms. 38 is somewhere in there. I am getting like 1.15, 1.16. Is that about what you came out? Perfect. Any questions on using the nomogram? I'm a number cruncher, so I'm going to end up using the formula. But that nomogram is there. On the test, anything that has a question about body surface area, I will use both and I'll give a range so that if your line's slightly off, I account for that in the solution. So if you're off by a little bit, if your line doesn't match up perfectly, we're good with that. So how is that used? Well, similar to the dosages based on weight, we have a recommended dose, a label that might tell us to use 30 milligrams per meter squared per 12 hours. And we have a patient that is 58 inches and, let's go 66 pounds. So our first thing we want to do is find their body surface area. (58) times 66 over 3131 square rooted. Second square root 58 times 66 divided by 3131. 1.11 that'll round to. 1.11 times 3131 divided by 3131. 1.11 times 66 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 divid meters squared. And now we'll go ahead and just use the 1.11 square meters over 1. Now we're going to use that to calculate their dosage. Meters squared on bottom, this is 30 milligrams per 1 meter squared. Meters squared cancels out. 33.3 milligrams over 1. That's our dosage, 33.3 milligrams. But you have to make sure we put back in per 12 hours. So I'm going to have you guys calculate a dosage quick. So for this medication, the label recommends 20 milligrams per meter squared for 8 hours. Patient who is 68 inches and 130 pounds. Calculate what that recommended dose would be. So our first step is to find the body surface area. 68 inches times 130 pounds over 3131. Get rid of 68 times 130, 131. 1.68 meters squared. So we start out 1.68 meters squared over 1 times 20 milligrams per meter squared. Squared cancels out at 33.6 milligrams every 8 hours. Any questions? Okay, it is time for a break, so let's go ahead and take a break. We'll come back at 11:30. We'll talk about safe doses, and then if we have any time left, we'll review for our test next year.
Oh my god, he does. Like, I always. I did. Yeah. I'm so happy for her. Yeah, that was like a crimson. That's almost. Yeah, she looks good. Her dress was cute. I didn't know that. I don't know. Dude, I didn't know. I didn't either. Yeah, you just. I know what people. Oh. Her nails are thin. Yes. Yeah, we have guinea pigs. Wild. Hmm? Yeah, you play with them. Oh, it's we love our hamster in the wall. Yeah, he's dead. The hedgehog climbed to an island. On an island. That climbing out was good. He had a cut a hole to get it out. Yeah, it was ticked. Yeah, and then, well, actually, the hamster got lost, but then 3 days later, we were scratching him. Oh, got it out. So he's sitting there with his arms open because he's so excited to be saved. But then, like, a couple weeks later, he went back. Well, it was my sister's brother. Yeah. She's a pet hoarder. Because she's got the rubber jacket. To me, it looks like a rotten banana. That's why it's called for that. And then she started horses really fat. Chicken nuggets. Chicken nuggets. And then she called it chicken nuggets.
Okay, it's that time, so let's go ahead and get rolling here. So we want to talk a little bit about safe doses. Safe dosage is all that is you're taking what a doctor has ordered and double checking it just to make sure it fits the guidelines on the label of the medication, the supply that you have. So where this would apply is if the doctor just orders a certain number of milliliters of the medication rather than the milligrams, and you need to go backwards to double check to make sure that that amount does not exceed what is recommended. So we're going to look for safe dosages. First of all, based on weight. So for a safe dose based on weight, let's say we have a doctor that has ordered 40 milliliters to be administered every 6 hours. For a patient, 77 pounds. Our supply, label tells us that it recommends 6 to 8 milligrams per kilogram every 8 hours. The to start off with, we completely ignore the doctor's order. We are calculating this as though we are calculating the dosage ourselves. So I have a patient that is 77 pounds, divide by 2.2, which gives us 35 kilograms. Now we start our work with that 35 kilograms. And we have, we're going to use the maximum, 8 milligrams per kilogram. Milligrams cancel out. I forgot to give you the rest of the label. That'll make this easier. The rest of the label says that this is constituted as 25 milligrams in 4 milliliters. So we've put in the 8 milligrams per kilogram here. We're going to convert milligrams to milliliters here. So we're going to put the 25 milligrams on bottom so that the milligrams will cancel out in 4 milliliters. The milligrams cancel out. On top here, 35 times 8 times 4. Oh, what do we have there? 1,120 milliliters. On bottom, we just have the 25. So divide that by 25. 44.8. Now, if we're not careful here, we look at the 40 milliliters recommended by ordered by the doctor and think that's less than 44.8. This is safe. What's the problem, though?
Hours.
The hours. This is every 8 hours. The doctor ordered every 6. We need to do a titration to convert this to 6 hours. That's 44.8 milliliters. It was calculated in 8 hours, and we're converting to 6. Times 6 divided by 8 is 33.6 milliliters every 6 hours. That is the max dose. We're going to go ahead and find the minimum dose just to complete the circle here. That 33.6 milliliters was calculated off the 8 milligrams per kilogram. Let's convert it to the minimum, which was 6. That's 25.2 minimum milliliters every 6 hours. So this is not a safe dose. The doctor's order exceeds the maximum recommended dose. So you would want to double check with the physician on that dosage. Next example, let's say we have a doctor that has ordered 5 milliliters to be administered twice daily. Patient, 88 pounds. Our supply says 250 to 300 micrograms per kilogram per hour. And it is constituted 5 milligrams and 2 milliliters. So as always, we start off, we have to make sure our weight is in kilograms. We're going to convert our 88 pounds, divide by 2.2. Our patient is 40 kilograms. Our calculation starts with the 40 kilograms over what? We're going to start out with the maximum dose. That's usually the one that we're worried about exceeding. That is 300 micrograms per kilogram. Kilograms cancel out. We are in micrograms. Now the rest of our label is milligrams to milliliters. So we need to convert those micrograms into milligrams. So the micrograms go on bottom so that they will cancel out. Remember, the milligram is the larger unit, so I put the 1 with the milligram. There are 1,000 micrograms in 1 milligram. That'll put us in milligrams, and from there we can convert. 5 milligrams on bottom, so the milligrams will cancel out into milliliters. Milligrams cancel. Let's multiply. So we've got 40 times 300, 1 times 2, 24,000 milliliters. On bottom, 1,000 times 5 is 5,000. We divide, we're going to get 4.8 milliliters. What's the time limit on that? Per hour. Doctor's orders, of course, is twice daily, which means 12 hours. So let's convert that 4.8 milliliters. This was converted per 1 hour. We're going to take it to 12 hours. $57.6 liters over 12 hours. It's our max dose. Let's find our minimum just for fun. $57.6 milliliters. It's calculated, bless you, off of 300 micrograms. Let's go to the 250. Giving us 48 is our minimum dose. 48 milliliters every 12 hours is the minimum. So I would really hope that the doctor maybe just misprinted their orders. Said twice daily. Because obviously 5 milliliters twice daily is way below recommended minimum. It's not dangerous, just probably not very helpful. Any questions on that one? Let's have you guys try one. Now, by the way, just a side note on this one. It gives that recommendation every hour. Most of the ones I've done so far, the example, the doctor's orders, the time frame has been smaller than the recommended time frame. That's generally safe. Give smaller doses more often is usually safe. To give larger doses less frequent can sometimes not be safe. So when the recommendation is per hour and the doctor's saying every 12 hours, that's something to check up on too. Even if the total amount given in that 12 hours is within the ranges, if you convert from the 1 hour, having one large dose like that might be too big of a shock as well. Okay, so the example I want you to try. Order is for 4 milliliters every 6 hours. for a patient who weighs 33 pounds. And the label on our supply is telling us 1.5 to 2.0 milligrams per kilogram a day. It's constituted as 50 milligrams, 25 milliliters. Check to see if that is a safe dose. Okay, so our first step is to convert that weight to kilograms. Divide by 2.2, 15 kilograms for this patient. Start out with 15 kilograms over what? We use the maximum, 2.0 or just 2 milligrams per kilogram. Cancels out our kilograms. Converting milligrams to milliliters, we have 50 milligrams that'll go on bottom in 25 milliliters. Canceling out kilograms. So on top there, we've got 15 times 2 times 25, which is 750 over 1 times 1 times 50 is 50. It's 15 milliliters. That is per day. Doctor's orders are for 6 hours. So what we have is 15 milliliters. That's the recommendation for a day, so that's 24 hours. We want to convert that to 6 hours. Times 6 divided by 24. It's 3.75 milliliters every 6 hours. Four milliliters exceeds that. Let's find the bottom end of the safe range just to finish it off. 3.75 milliliters is off the top end of the range, calculated off the 2.0. Let's find the 1.5. There's 2.81 liters every 6 hours is the lower end. So again, that 4 milliliters every 6 hours recommended by the doctor is outside of the safe range. You would want to double check. Let's double check safe dosages for IVs. Let's say the doctor has ordered to run an IV 20 drops per minute. Patient, 66 pounds. Supply, label says 8 to 10 milligrams per kilogram per hour. Constituted 25 milligrams in 8 milliliters and a drop factor. $12 drops per milliliter. So again, we're going to ignore the order and just go with what we know about the patient and calculating the safe dosage based off of that. So we're taking the pounds divided by 2.2, give us that our patient is 30 kilograms. Now, we haven't done IVs combined with dosages based on weight yet, so this will be a little bit different for us here. We start off with that 30 kilograms over 1. We're going to use the maximum dose again, 10 milligrams per 1 kilogram. Kilograms are gone. Now we are going to convert that 25 milligrams, 8 milliliters, so the milligrams are gone. Before we do a drop factor, we're going to calculate this out to get a dosage. This is 30 times 10 times 8, 2,400 milliliters. 1 times 1 times 25 is 25. Divide that out, 96 milliliters. The reason we wanted to do that is because we need to attach a time to this for our drop factor to have much meaning. What time are we going to attach with this? Per hour. That's 96 milliliters per 1 hour at this point.
Where did you get the 8 milliliters from?
25 milligrams and 8 milliliters. That's our supply. Yep. So once we attach the 1 hour time frame to our 96 milliliters, now we'll do our drop factor. I want to move down a step here because we're getting a little crowded. 96 milliliters per 1 hour. We have our drop factor. 12 drops per 1 milliliter. So the milliliters are gone, but this is going to put us in drops per hour. So we want to get rid of those hours. Turn it to minutes. Put 1 hour on top so that the hours will cancel out, going to 60 minutes. Hours cancel out. Now let's calculate our drops per minute. So 96 times 12 on top gives us 1,152 drops over 60 minutes. It's 19.2 drops per minute. That is the maximum dosage for this patient. Let's find the minimum dosage. We can titrate drops per minute, just like we can anything else. It's 19.2 drops per minute. That was calculated using 10 milligrams per kilogram. We want to change it to what it would be for 8 milligrams per kilogram. 19.2 times 8 divided by 10, 15.36 drops per minute. So the maximum, 19.2, the minimum, 15.36. Doctor's orders of 20 drops per minute are slightly outside of that range, so you would want to double check before you administer. Those are a little bit more confusing. Let's do one more example. So let's say the doctor orders to run an IV. Oops, you have a question? Doctor orders to run an IV at 45 drops per minute. Patient that weighs 198 pounds. So the label of our supply says 6 to 8 milligrams per kilogram per hour. Label says the supply is constituted at 15 milligrams in 4 milliliters. Drop factor of 15 drops per milliliter. So we always start out with the patient here, converting that pounds to kilograms. So divide by 2.2. Giving us 90 kilograms. Start out with 90 kilograms. So we're going to do our maximum again, the 8 milligrams per kilogram. Cancel out our kilograms. We currently have milligrams on top, so to get rid of that, use our supply here of 15 milligrams. 15 milligrams goes on bottom in 4 milliliters. 4 milliliters goes on top. Canceling out the milligrams. So at this point, let's go ahead and calculate what this is in milliliters so that we can put our time frame with it. So we have 90 times 8, 4,880 milliliters per 15. It's 192 milliliters. So we'll put our time frame here of 1 hour. That. So 192 milliliters an hour is the recommended dosage from that supply. So we go with the 192 milliliters per hour, and we're going to convert it into drops per minute. We have a drop factor, 15 drops per milliliter. Milliliters are on top, we want milliliters on bottom. They cancel out. Now I have drops per hour, so we want to cancel out the hours. 1 hour on top, so it'll cancel out, is 60 minutes. Hours now cancel out. 192 times 15 drops, 2,880 drops for 60 minutes. What does that come out to be? 48 drops per minute. That's the maximum flow rate. Let's find the minimum flow rate by titrating that 48 drops per minute. That was calculated at 8 milligrams per kilogram. It's our maximum dose. We want to convert it to 6 milligrams per kilogram, our minimum dose. Gives us 36 drops per minute. Is the minimum recommended flow rate. So the doctor at 45 drops per minute is within our range. Any questions there? Too many to ask. The last safe dosage calculation we want to look at is safe dosages for dosages based on body surface area. Let's say I have an order for 2 milliliters to be given every 8 hours. Patient, 70 pounds and 47 inches tall. Our supply label says 7 to 8 milligrams per meter squared per day. Constituted 5 milligrams in 4 milliliters. So when we're working with body surface area, the first step is not to convert from pounds to kilograms, it's to convert from height and weight into square meters. Then we have 47 inches tall times 100 or times 70 pounds. Divided by, since those are standard, so we divide by 3131. Square root of 47, 70, 31, 31. Have a good week. Gives us 1.03 square meters. It's our body surface area. So 1.03 meters squared is where we start our calculation. Here's the maximum of 8 milligrams meter squared. Squared's canceled out. Our supply is constituted 5 milligrams. That goes on bottom, so it cancels out with the milligrams. In 4 milliliters. So we multiply 1.03 times 8 times 4 to 2.96 liters, or 5, so we divide by 5, is a 6.59, we'll round that to 2 digits. 6.59 milliliters, that is per day. Doctor's orders were 8 hours. Do that titration. 6.59 milliliters, that was calculated per day, so I'm going to put in 24 for 24 hours. We're going to titrate that to the doctor's orders of 8 hours. 6.59 times 8 divided by 24. This is 2.20 milliliters every 8 hours. It's our maximum recommended dose. Take that 2.2 milliliters. We're going to titrate it to get the minimum dose. The 2.2 is off the 8 milliliters per meter squared. The minimum was 7 milliliters per meter squared. Take the 2.20 times 7 divided by 8. 1.95 or 1.93 if we round that off. 1.925 rounds to 1.93 milliliters per 8 hours. The minimum recommended dose. So 1.93 to 2.0, the doctor says 2, that's in the middle of that range. What do you think? Not horrible? I think you guys have suffered enough for the week. So let's give you some topics here that I want to make sure you have reviewed. First of all, pages out of the book. Page 188 through 190. Another page here I want to make sure to have. Start on page 184, 1 through 11, the odd, just to make sure you've done that one. And that one we looked at last week as well. Page 188 to 190 is the dosages based on weight. We looked at that last week a little bit as well. 1 through 21, the odd. The newest one, based on body surface area, page 196 to 197, 1 through 19, the odds. So, a couple of things I want to make sure we review for the test. Let's say that we have an order for 800 milligrams of Motrin. Look at your supply. Your supply is GRIV tablets. You need to figure out what you're going to give to the patient here. Start out with that order of 800 milligrams. Put it over 1. Our supply, though, is in grain. So the first thing we have to do is convert that milligrams into grains. What is our relationship between milligrams and grains? Grains are larger. 1 grain is how many milligrams? Anybody remember? It's 60 milligrams. Good. So the milligrams cancel out. Now we can go ahead and convert to tablets. This GRIV tablet is saying that 1 tablet is equivalent to 4 grains. So we're going to put the 4 grains on bottom so that the grains will cancel out. 1 tablet on top. Now we multiply 800 times 1 tablet, 800 tablets. On bottom, 1 times 60 times 4 is 240. We'll take the 800 divided by 240, 3.33. Or 3 1/3 tablets. We had mentioned when we started talking about medications that tablets, especially if they're labeled as scored tablets, can really only be administered in a full tablet or a half tablet. So, if we have to go to the nearest half tablet, this is between 3 and 3.5. Is it closer to the 3 or closer to the 3.5? 3, yes. This would be 3.0. This would be 3.5. The middle would be 3.25. 3.3, somewhere in here. It is closer to the 3.5 tablets. So being able to round to the nearest half tablet is something you need to be able to remember. You need to remember how to do. Any questions on that problem? Be very careful, by the way. GR, remember, is grains. It's a very common mistake to see GR and think grams. For grams are just G. Let's say that we have an order.
Yes.
For
4 grains in 1 tablet.
120 milliliters.
No. The other way around.
Our supply.
Hmm?
That's what it
Is an OZXII bottle. I want to know how many ounces, how many fluid ounces to administer. What does this mean? OZXII bottle. 12 ounces. Very good. XII, that's 1011. That's 12 ounces. All that's telling us is that that's a 12-ounce bottle. Does that tell us anything about the concentration or any of that? No, there's no rate there. But we do ask how many ounces to administer. All that's asking us to do is to take 120 milliliters and convert it into fluid ounces. Remember, if you look up on your conversion tables, 1 fluid ounce is approximately 30 milliliters. The milliliters cancel out. This is 120 fluid ounces. 30, 120 divided by 30 is just 4 fluid ounces. So it ends up being just a conversion problem. Really not much to do with dosage calculations at all. Other things to make sure you remember. How to work with our percent solutions. Weight in weight, volume in volume, and weight in volume solutions. Remember those. Remember our concentration adjustment formula, C1V1 equals C2V2. That one comes up. And of course, dilutions is huge. We spent the first class and a half basically on dilutions for this unit. Remember a dilution? I have a 1 in 5 dilution. That means 1 part serum, 5 parts total solution. Any questions? This is a long unit because I feel it's the most important unit of the course. Next week, we'll take the test in the first hour. I'll probably wait till about 11:40 next week. I'll give you an extra 10 minutes. This is a little bit longer test. You may want to come in early and start on it a little bit earlier. I'll make sure that the other campuses know that you can start anytime after the campus opens for the morning. But at about 11:40 next week, I will start lecturing on Unit 4, which is talking about graphing. Units 4 and 5 are kind of that preparation for the next level of what you would need if you go on to the bachelor's degree. Okay, well, you guys have a great week. We'll see you next Friday.